Thank you for tuning into Dyno Insights. In this episode, Mike and Chris will be discussing eddy current dynamometers.
Well, hi Mike, good to see you.
How's it going, Chris?
Doing well, thanks. Last time we were here, we were talking about the water break and getting into some details there.
Yep.
Today, I'd like to understand more about the what's referred to as the eddy current dyno.
Mm-hmm.
Perhaps you can give a bit of an explanation, a bit of background on that.
Yeah, I mean, just to talk a little bit about the naming convention of an eddy current dynamometer. So that's the popular word typically used when you're describing it, but officially, it's officially called an inductor dynamometer. And there's several companies, including Froude, our company, where we'll call it an eddy current, but mainly we'll call it by its model number, model name, which is an AG, standing for air gap. So there's lots of different naming conventions for it, but eddy current is the popular.
Hold on a moment. When you say air gap, how does the air gap fit to this?
It doesn't,
Okay.
except for what the AG stands for.
So how did it get that name?
Good question. I can't answer that.
Okay, so within the Froude history, it developed a name.
It did.
That's interesting in itself. But
There's a lot of names that we probably don't know how it originated, but it did.
Okay, but if we say with eddy current as the most popular name, that seems to be a good way to go.
Yeah. Yep.
Perhaps you can talk a little bit about where it's used, what sort of applications you'd see for an eddy current dyno.
Sure. So, in my past life, I've used a lot of eddy current dynamometers, and the industries that I worked in were mainly automotive, diesel industries, so it'd be mainly on-highway type vehicles or engines, and also a little bit of the off-highway, so the brand names Caterpillar, Cummins, John Deere type engines where the eddy currents were used.
So that's interesting, but what type of testing would that be applied to?
So with the eddy current dynamometer, it's applied mainly to steady state type testing, where there's step changes and you're concerned more with the controllability over that steady state point versus the ramp going up or the ramp coming down. Now, I will say it's not exclusive to just that. There are situations where the eddy current dynamometer can accomplish that task to a certain point, like any dynamometer type.
So I've never used an eddy current myself, but I've seen them in factories at the end of line testing for engines, or I think sometimes for catalyst characterization or engine endurance testing like that.
Yeah, that's a real popular one. So if you've been in the test cell business in the automotive industry and you've been exposed to engine emissions work, you would have heard the term catalyst aging or catalyst development. And eddy currents were a strong part of the supply of equipment that was required to conduct some of this testing. And the reason being is that it was a steady state test initially, where we had to accumulate hours to simulate the hours or the vehicle mileage of what a catalyst would see. And it was perfect for it because it had good control over steady state conditions and it was robust.
So it's really more suited to endurance testing and that, shall we say, the simpler test cycles than performance testing or emissions testing.
Yeah, exactly, Chris. I think for 90% of the eddy current dynamometer installations that I've seen, it was related to steady state durability testing.
Okay. So if I wanted to find a dyno, what would I be looking for? What features should I be looking to include?
Well, that's a good question because I've seen an array of different types of dynamometers. And I've worked with the older ones, and usually with the older dynamometers, eddy current-wise, they're higher inertia dynamometers. Today's technology and the drive or push to increase the capability of an eddy current dynamometer to make it more versatile have come up with the lines have gone to what we call low inertia dynamometers. So the inertia is drastically different, and that allows you to do some of the more transient step changes on the D cells along with the X cells. So a light inertia dynamometer allows you to get to point A to point B faster.
Okay, so if I was looking to acquire a used dyno, for example, then there may not be such a wide range available if there's been technology changes, but it sounds like I should look more toward a later one with a lower inertia, perhaps.
Yeah, if you were making an investment in an eddy current dynamometer and you weren't certain of exactly what your testing was going to be for the next 10 years, you'd want to go with a newer style dynamometer because of that inertia factor. So it's just as robust as the old. It just gives you a little bit more capability because of the lighter mass that you're spinning in the dynamometer.
Okay, that's interesting. What's the biggest advantage of this type of dyno?
I think it would be its sweet spot is in the 0 to 10,000 RPM range, and I wouldn't probably go anywhere above 1,000 horsepower. So in that range, its sweet spot is it's cost effective in regards to its low maintenance. It's also infrastructure wise, there's not a lot of cost involved with setting up an eddy current dynamometer. If you were to compare to other dynamometers, if you had a brand new test lab and you had to make an infrastructure investment, if the eddy current fit in with the range I talked about, it would probably be less costly overall from a capital budget perspective.
So this is an electrical machine, but it would require a water supply as well for cooling, or is that not necessary in all eddy currents?
You bring up a good point, Chris. I think the biggest thing with the eddy current dynamometers, you will require electrical and you will require cooling. It's the amount of cooling in comparison with other dynamometers. So if you were talking, there's a big difference between a water break and an eddy current in regards to water requirements. From a power perspective, electrical perspective, that's the main driver in an eddy current dynamometer. You're feeding current to the coils of the dynamometer itself. It's fairly low compared to, say, for example, an AC dynamometer, which is hundreds of amps. It's nowhere near that with an eddy current dynamometer. So the infrastructure costs to set it up are fairly cost effective.
Yeah, so what you described to me is a machine which is more typically used on steady state testing. So what do you see as the future for the eddy current dyno?
Well, I see it changing in regards to just increasing the capabilities of it. So like we talked about with the low inertia, that's one thing that's changed. And again, it's relatively speaking in from a time frame perspective, but it has changed. I think it's just the application of it that's going to change. I don't think they're going to go away anytime soon because they've got their sweet spot, just like a water break or a hydraulic dynamometer has a sweet spot. And I think there's so many applications out there that an eddy current would work with. I don't think they're going away. I think the push will be probably a higher speed, higher power. I think that would be the push. But right now, once you get above relatively 1,000 horsepower, or you're talking about the costs go up exponentially to create a eddy current dynamometer capable of spinning at higher power and higher speeds.
And given that this is an absorbing only machine, suppose it could be modified the same way as we've talked about for the water break with some additional equipment such as a motor to overcome certain characteristics.
Yeah, that's another good point that you bring up. Again, it's the application of the type of testing that you need to do. So when we talk about, there's a list of questions you need to be able to ask and get answers for to really select the right dynamometer for your use. But when it comes to adaptations to it, so I can go back quite a few years to talk about a brand of dynamometer that had a motor attached to it as a product. So you bought it with the ability to spin up to 3,600 RPM. But that worked great when you were doing simple tests like friction testing, where it was a steady state speed you needed to maintain. But it still had its limitations, but it got you one step closer. So yes, there have been adaptations to it where you put an AC motor on the back of it. People put starter motors on the back of the dynamometers itself, so some of the engines they test may not have a starter with it, so you have that versatility. So there's a lot of different ways of utilizing an eddy current dynamometer.
Okay, so we've talked about the infrastructure requirements for an eddy current dyno.
Mm-hmm.
What about the maintenance side?
Yeah, that's an important point. With the maintenance on a eddy current dynamometer, you're going to typically have water flowing through it. So as a water break dynamometer, there's certain things you need to do. So water quality is still important. You also need to have proper filtration. So maintaining that is one of the key things.
Is that as a stricter requirement as on a water break?
It is not as strict as a water break.
Okay.
I think we've both had some experience in regards to our exposure to that, and I can tell you that yes, a water break's lifeblood is water. With an eddy current dynamometer, it's a combination of mainly current, power flowing through it, plus keeping it cool as it heats up. So that's one of the aspects of the maintenance part of it. But, it's not just water, it's also the lubrication system. So you have a simple drop feed system that drops so many oil drops per minute on the bearing, and you just need to make sure that you maintain the filtration with that too. So it's fairly straightforward. There's not a lot of maintenance beyond that. It's just general, typical maintenance that you expect with any rotating machinery then after that.
Yeah, still talking about a relatively high-speed machine. I think you mentioned up to, about 10,000 RPM?
Yeah, in the ballpark, yep.
Yeah, so that's certainly quite fast for a normal roller bearing in these machines?
Yep, they're typically roller bearings, ball bearings, depending upon the style of dynamometer it is and the loads being placed upon it, hub loads. And again, Chris, that's probably another question that goes into the question and answers that you ask as far as what are you hanging off the end of that, because it is a rotating device with bearings and they only can take so much load, overhung load and mass on it. But that's less maintenance. It's more asking the right questions.
But if these are used in automotive and sort of light truck applications, would the flywheel, for example, would normally be part of the engine and then driving through a drive shaft to the dyno?
Yes, yeah. But actually, we've had applications, or I've seen applications where we actually had flywheels mounted to the dynamometer. So, and those were used for two purposes. One, if they needed additional inertia, or two, if it was set up with a ring gear on it so you can attach a starter to it to actually spin the dynamometer and start the engine.
Oh, that's great.
So from a maintenance perspective overall, Chris, it's fairly low maintenance. There's not a lot to do beyond keeping the filters clean and changed, keeping the water system clean, and keeping your chemical treatments process up to speed as far as the water going through it if it's a recirculatory system.
Well, which fits to your comment earlier about it being relatively small infrastructure implications.
Mm-hmm.
Okay.
Exactly.
Oh, that's great. It's interesting when you talk about the questions to ask. It seems like when you're commissioning a test cell, there are a range of questions we need to go over, and I think that's something we'll probably cover in a future podcast.
Yeah.
But it's certainly quite a complicated subject sometimes.
Mm-hmm.
I think in this case, and the discussion's been useful in understanding the type of testing that current's used for, understanding where its strengths and weaknesses are. And please ask that you stay tuned for future podcasts and where we'll move on to discuss the AC dynos and test cell applications.
Sounds good, Chris.
Okay, thanks, Mike.
You bet.
Thank you for listening to Dyno Insights presented by Froude. If there are any engine testing topics you'd like us to discuss, we'd love to hear from you. Please email us at podcast@froudedyno.com.